Hi there. So we are proceeding the Fourier analysis series, and in this video we are going to talk about the discrete Fourier transform. Right then. The motivation to discrete Fourier transform comes from the feasibility of the Fourier transform in practical applications. I mean, if you're in a laboratory and you have a cord with an electrical signal flowing through this cord, and you might want to know what's the spectrum of the signal. Now, the thing about Fourier transform is that it requires an analytical expression of this signal in order to evaluate its spectrum. But you don't know what an x of t is. You don't know its analytical expression. The signal may be completely random. It comes from, I don't know, maybe a sensor. So that's how the Fourier transform is useless in practical applications. So we are going to evaluate the spectrum using a computer. Now, the thing special about a computer is that it works with discrete signals rather than continuous signals like the one we have. So we have to sample the signal. So assume this is x of t. We have to sample it into a discrete signal, and then we will use our computer to evaluate the spectrum. Now this process is called sampling, which is basically a process of taking certain samples of the original signals at an adequate rate called Fs, which is the sampling rate. And this sampling rate is determined by something called Nyquist sampling criterion. This criterion basically ensures that the discrete version is a good representative of the continuous signal. In other words, we can recover the continuous signal from this discrete version. So here comes the discrete Fourier transform. It is a modified transform that is specifically designed to handle the discrete signals and will be executed by this computer to get the spectrum of this discrete signal. But hey, we wanted the spectrum of this signal, not this signal. There's a different signal, and that's why it has a different spectrum. Yes, that's right, and that's why we will study the relation between the spectrum of the discrete version of a signal and its original continuous version. Or in other words, we will try to evaluate the spectrum of the discrete version in terms of the original spectrum. So this is the outline of this lecture. We have discrete Fourier transform, Nyquist sampling criteria. And remember why we had to use this computer, because computers have finite memory. Let's say a RAM of, I don't know, 6 megabytes. So it can store up to a finite number of numbers. So that's why we had to sample the signal. So now we'll go through some boring details, but keep this outline in your mind. Right then, let's begin with the sampling theorem. Mathematically, the sampling process is defined by multiplying the continuous signal, let's call it x of t, by a train of pulses. spaced with interval called Ts. So this is the sampling train, let's call it, I don't know, S of t, which is defined by summation delta of t minus nts. So if we multiply x of t by the sampling train, we'll get the sampled version of x of t. Let's call it xs of t. So this is presumably a representative of x of t. Now let's try to evaluate the spectrum of x sampled of t by applying the Fourier transform. So Fourier transform of xs of t, this is equal to integration. Xs of t is basically x of t dot summation delta of t minus nts, which is the sampling train. So this is x of t times e2 minus j 2 pi ft dt. Now, I don't know if you're familiar with impulses function and their basic properties and how to evaluate integrals involving impulsive functions. This is very simple actually, and if you're not familiar with them, you can check the Wikipedia article of impulse function. This is simply equal to, let's just interchange the summation and integration operators first. So this will be summation and then integration for x of t delta of t minus nts e2 minus j 2 pi ft dt, and this is simply equal to x of nts e2 minus j 2 pi f nts. Let's call this x of f, the spectrum. Now this is called the formula of discrete Fourier transform. Well, actually the discrete time Fourier transform, to be accurate. Because we're still somehow still related to the time domain by this factor of Ts, and when we get rid of it, we will get the discrete Fourier transform. But I guess that's a different topic. So basically what we have done is that we've created a transform that is specifically designed to handle discrete signals like this. And we call it the discrete time Fourier transform. We don't have to repeat this simple derivation each and every single time we encounter a discrete signal. We just directly use the discrete time Fourier transform. Notice that x of f represents the spectrum of the discrete signal, while the spectrum of original signal, let's call it x of f. This is different from xs of f. I will try to find what's the relation between them. But for the moment, I'll try to point out some important notes about the discrete time Fourier transform. First of all, xs of f is a periodic function, that is periodic in the frequency domain. And how do we know this? Because basically we're adding up a bunch of e2 minus j 2 pi n f nts. You can see x of nts is just the magnitude of these samples, so it doesn't really affect the pattern of xs of f, since it's not a function of f. This is basically determined by this e2 minus j 2 pi f nts. This is actually similar to what we saw in the Fourier series. If you remember the synthesis formula from the Fourier series, where we had x of t equal to summation c sub n e to plus j 2 pi n f naught t. We were adding harmonics, frequencies multiple of f naught when n equal to 1, actually from minus infinity to infinity, 1, 2, 3, 4, 5, and that's how we get f naught, 2f naught, 3f naught, and we add up all these sinusoidals, each one with a different magnitude, and we ended up with getting x of t, which is basically some periodic functions. So this similar what's happening here. We're also having same summation, but just it's different variables. And instead of nf naught, we have nts, and instead of t, we have f. So it's basically similar to what was going on in Fourier series. So instead of getting x of t, a periodic signal in time domain, we are getting x of f, which will also be a periodic signal, but in frequency domain. This is an obvious analogy that you can notice by comparing these two formulas. Okay, now so we have to understand the relation between x of f and xs of f, where xs of f is the spectrum of the sample signal and x of f is the spectrum of the original analog signal. So to do this, we have to evaluate xs of f, which is the Fourier transform of xs of t, which equals to the Fourier transform of x of t, the original analog signal, multiplied by a sampling train at a rate of ts sample per second. Now, if you remember, we've done this earlier here, and in the end of this simple derivation, we got a formula for DTFT. But this time, I will do it in a way that reveals the relation between xs of f and x of f. So this equals to, according to one of the most important properties of the Fourier transform, this equal to the Fourier transform of x of t convolved with the Fourier transform of the impulse train. So this dot product is replaced by a convolution in the frequency domain. So to proceed, we have to understand how to evaluate the spectrum of this impulse train. And to do this, I have a very interesting method of evaluating the spectrum. I will do it graphically. So look at this. I'll plot a cosinusoid, with a 1 Hertz frequency. So this is cosine 2 pi x, which is a 1 Hertz cosinusoid. Okay, now I'm going to add to this cosinusoid another cosinusoid with a 2 Hertz frequency, so 1 Hertz plus 2 Hertz. That is 4 pi x. Okay, so we have cosine 1 Hertz plus cosine 2 Hertz. Now I'm going to add another cosinusoid with a 3 Hertz frequency and see what we get. So plus cosine, that is 6 pi x. So 1 Hertz plus 2 Hertz plus 3 Hertz, and that's how it looked like. Interesting. Do you know what is the value of the signal at these peaks? It's actually 3. Here and here and here. Here at 0 second, at 1, at 2, at 3, at -1, at -2. Because when x equals 0, this is cosine 0, and here we have cosine 0 as well, and here we have cosine 0, regardless of its frequency. So we have cosine 0 is 1, so 1 plus 1 plus 1 is 3 when x equals 0, and when x equals 1, when x equals 2. Let me add up more and more cosinusoids. I will add, so I'll add 4 hertz, that is 8 pi x plus cosine 10 pi x. Okay, let's look at it. So the peaks are increasing their values. Now the value of each peak is 5, since we have 5 frequencies. And guess what? What's going to happen if we continue to add up frequencies of 5 hertz, 6 hertz, 7 hertz, 8 hertz, up to infinity? What's going to happen? Okay, these peaks are going to have a value of infinity, and these minor fluctuations are going to disappear gradually. So what I'm trying to say is that the plot of the function will be like this: an impulse at 0, and an impulse at 1, an impulse that have a value of infinity. Okay, at 0, at 1, at 2, that's what we saw, and so on. That is the time axis, and at -1, at -2, and -3, and so on, which is the sampling train. So we can call this signal xs of t. And what I'm proposing is that the spectrum of this signal, as we have just seen, is that the spectrum of this signal is, do you remember what frequencies did we use to get the signal? Yes, we used a 1 hertz. This is the frequency axis, so let's just call this x. So this is the sampling signal. Let's call it s of t, sorry. I think we called s of t. Yes, s of t, which equals to summation from n equal minus infinity to infinity, delta of t minus n. So delta of t minus, so this is delta of t, and this is delta of t minus 1, and this is delta of t minus 2, and so on. And when you keep adding up these impulse function, you get s of t, the sampling signal. And how did we get this signal? We got it by adding a 1 hertz. So let's just call this s of f, which is the spectrum of s of t. We added up a 1 hertz sinusoidal, which had a peak of 1, and a 2 hertz, which has a peak of 1 again, and a 3 hertz, and a 4 hertz, and we kept adding up these frequencies. So 4 hertz, 5 hertz, and so on. So this is a frequency axis. And even if we added the negative frequencies, like we added cosine 2 pi t plus cosine 4 pi t plus cosine 6 pi t, and so on. Even if we added plus cosine minus 2 pi t, so that is a -1 hertz, -1, and -2, at -3, so that is cosine -4 pi t plus cosine -6 pi t. So basically, because cosine function is an even function, so cosine -2 pi t is equal to cosine 2 pi t, and cosine -4 pi t is equal to cosine +4 pi t. So it will not affect the plot of the signal in the time domain, even if we added these negative frequencies, because the cosine is an even function. So if you remember, all these kind of cosinusoids have a factor of 1, 1, 1,
So the magnitudes are 1, even if we add plus cosine minus 2 pi x, minus 2 pi x, and then plus cosine minus 4 pi x, and so on, the plot will not change at all. Okay. So that means that we have proved the spectrum of S of t is S of f, which is this function. We have proved this graphically, and you have to prove it analytically using Fourier series, because S of t is a periodic function in time domain. Use Fourier series to evaluate the spectrum S of f, and I'll give you the answer. S of f equal to maybe 1 over ts summation 1 e2 plus j2 pi n t. Yes, n t. So Cn is equal to 1. This is Cn. And I'll give you the answer for the homework. The homework is to evaluate the Fourier series of this signal of t minus nts, and we took ts equal to 1. The answer will be S of t equal to 1 over ts summation 1 e2 plus j2 pi n fs, which is 1 over ts t. So Cn is equal to 1, C sub n equal to 1. I mean, the magnitude of all these frequencies is 1. 1, 1, 1. For all n values. So that is Cn equal to 1. And if you're wondering how are we going to get S of t, which is a real signal, by adding up a complex sinusoid like e to j2 pi nfst. So the answer is obviously, because the sinusoids are going to cancel each other. I mean, sine 2 pi t when going to be added with j sine minus 2 pi t. They are going to cancel each other because sine minus 2 pi t is minus sine 2 pi plus t. So the sinusoids are going to cancel each other. Only cosinusoids are going to add up to construct S of t, which is a real signal. If you're confused at the moment, that's because you haven't understand the Fourier series well. And if you're confused, you are recommended to watch my plus 40 minutes Fourier series video before proceeding this video. So to summarize this, we got the Fourier transform of the sampling train summation delta of t minus n from equal minus infinity to plus infinity is simply this spectrum. 1 Hertz, 2 Hertz, 3 Hertz, and 4 Hertz, with all having a magnitude of 1, even at 0 Hertz, minus 1, a minus 2, minus 3, and so on. So this is S of f, which can be analytically expressed by summation delta of f minus 1, of f minus n, from n equal minus infinity to plus infinity. So this is the spectrum of the sampling train. They are quite similar, actually, time domain and frequency domain, because C sub n appeared to be equal to 1 regardless of harmonic index value n. So for n equal 1, it equal 1. For n equal 2, it equal 2. For n equal 3, equal 1 again, sorry. So c sub n equal to 1 for all n values. Before proceeding our original derivation, I would like to generalize this formula to all TS values. I mean, what is the Fourier transform of summation delta of T minus NTS? So in our previous example, we took TS equal to 1. So that's just 1n. We want a formula for all TS values. Actually, we'll go back to our graphical method. You see, the time domain plot, we got impulses spaced by an interval of 1. This is an impulse when t equals 1. Let's just add a 0 frequency. So that is 1. 1 plus, so this is 0 hertz, 1 hertz, 2 hertz, 3 hertz, and so on. Okay, 1, 2, 3, 4. Let's plot it. These tiny fluctuations were a negative region. Now they are positive values. But anyway, they are going to disappear when we add up an infinite number of harmonics. Okay, so when t equals 0, we have an impulse. When t equals 1, we have an impulse. So in time domain, we have, this is the time domain, we have impulses spaced by a 1 second interval. So why is this happening? Why is the space between time interval between two impulses is 1 second? That is because the fundamental frequency I used have a 1 hertz frequency. Let's have another series with a fundamental frequency of 0.5 hertz. So 0 hertz plus a 0.5 hertz sinusoid. So we are going to add up multiples of 0.5. So 0, 0.5, now 1, plus 1.5, 2 pi times 1.5x, plus 2 hertz, so 0, 1, 1.5, 2 pi times 2x. Okay, I think that's enough. So 0, 0.5, 1, 1.5. Oh, we miss a cosine. A cosine 2 pi times 1.5x. Okay, that's it. 0, 0.5, 1, 1.5, 2, then 2.5, then 3, 3.5. Look at this. Now, the time interval between each two subsequent impulses is 2 seconds instead of 1 second. That is because the fundamental frequency have a frequency of 0.5 hertz. So the time interval between each two adjacent impulses is 2 seconds. So that means the Fourier transform of a train pulses having a TS separation is simply equal to, the Fourier transform of this impulse is simply equal to summation delta of f minus nfs, where fs equal to 1 over ts, from n equal minus infinity to infinity. So the spectrum of this is, using Fourier transform, appears to be, again, at 0 hertz, then at fs hertz, which is 1 over ts, then at 2fs at 3fs, at 4fs, and so on. So with this generalization, we can go back to proceed our original derivation. But remember, this can be proven directly by the homework, the analytical derivation of this. So back to our original derivation, we are trying to evaluate the relation between xs of f and x of f. And we took advantage of the property, of an important property in the Fourier transform, which is the relation between a product in the time domain and in the frequency domain. We compared the product into a convolution. So let me write it again. Xs of f, which equals to the Fourier transform of xs of t, which is x of t dot s of t. This equals to Fourier transform of x of t convolved with the Fourier transform of s of t, which is summation delta of t minus nts. So let's write s sub t s of t. Okay, so the Fourier transform of x of t is simply x of f. So here is the advantage of this derivation, which will reveal the relation of x of f and xs of f. So x of f convolved with the Fourier transform of s of t, which we have shown earlier that it is equal to summation delta of f minus nfs. There are a couple of ways to evaluate this convolution. One of them is, I'll do it graphically first, and then I'll do it analytically. So basically, this summation is a series of impulses this frequency, and this fs to fs, and so on. So we have to convolve this with x of f. X of f, let's just assume a general random pattern for it. Let's say this is x of f. And I'll illustrate later why I have chosen this pattern. So we have this to be convolved with the signal. If you are familiar with convolution and impulsive functions, this is the result of the convolution, which is x of f, to convolve this and this. And the result should look like this. At fs, another replica. At 2fs, another replica. At minus fs, another replica of x of f. If you're confused or wondering how this happened, I recommend you to watch my next video about the convolution and the impulsive functions. So this is coming soon. But for the moment, I'll try to do it analytically. I'll try to evaluate this convolution analytically. The convolution is defined by integration from minus infinity to infinity. We'll convolve this, so summation delta of lambda minus nfs convolved with x of f, so this will be x of f minus lambda t lambda. And by interchanging the order of summation and integration, we are about to convolve delta of lambda minus NFS with x of f minus lambda d lambda, which equal to summation equal minus infinity to plus infinity x of f minus NFS. So finally, this is xs of f formula that reveals its relation with the original spectrum x of f. Okay, now so it's the time to interpret this formula. This has something to do with the Nyquist sampling criterion. So we had x of t, the original analog signal, and we had to sample it because the computer only deals with discrete signals, and we got this. Then in the beginning we needed the spectrum of this signal, x of t. We needed spectrum, which is x of f. We don't know what x of f is, but we used the discrete time Fourier transform at a computer to evaluate xs of f, which is the spectrum of the discrete signal. And here we have the relation between x of f and xs of f. So what this formula telling us is that xs of f is basically a sum of replicated shifted versions of x of f. So if x of f look like this, then xf of f is x of f when n equals 0. So x of f when n equals 1, x of f minus fs. So at fs frequency we have another x of f. So this is x of f minus fs. And this is x of f. And then we have at 2fs we have x of f minus 2fs. And then we have at minus fs we have x of f plus fs, and so on. So this is the original spectrum, and this is the spectrum of the sampled signal xs of f. So if we neglect those replicas and focus on this fundamental part of the signal, it is similar to original spectrum. Now we are going to address the principle of Nyquist sampling criterion. If we assume that this signal has a spectrum, which is obviously a band-limited spectrum, having a maximum frequency of FM, Hertz. So this is the frequency axis, and this is the maximum frequency in the signal. Then the criterion tells you that the sampling rate, okay, Fs, which is 1 over Ts, this is Ts, the minimum sampling rate required should be greater than or equal to twice maximum frequency. Why? We can take a special case of Fs equal to 2Fm, which is the minimum sampling rate required to sample a signal having a Fm maximum frequency. So we have xs of f, the spectrum of the sampled signal, equal to x of f plus x of f minus fs plus x of f minus 2fs, and so on. And here we have x of f plus fs, and then x of f plus 2fs, and so on. let's look at the first replica. So if the maximum frequency is Fm, okay, and then we have, this is x of f, and then we have x of f minus fs, so this is fs, remember this is the bandwidth, which is 2fm, we will have, this is the second replica, or actually the first replica, x of f minus fs, this is 2fm again. Now, if the sampling frequency is reduced, or the maximum frequency Fm is increased, there will be interference between those replicas. We will have something like this. This is Fm, and this is Fs. And then, remember, we have to add up all these replicas. So you will get a distorted excess of f. These two parts are going to be add up, okay? Then you get a distorted spectrum that has no obvious relation to the original spectrum, x of f. This is going to disappear somehow. Now, it's also obvious why we have assumed that x of f looks something like this, or any other pattern, but limited between two frequencies. That is, x of f is called a band-limited signal, because it has to be band-limited. If it's not, let's just assume that x of f is something like this. Okay, this goes to infinity without degrading sufficiently. If this is x of f, then excess of f, which is x of f plus, this is fs, x of f minus fs, and x of f plus fs, and x of f minus 2fs, and x of s plus 2fs, it will be a mess. And you cannot extract x of f from it. You have to add all these replicas together, and then you'll get something that you'll never be able to extract x of f from it. Unlike with a case where x of f was band limited, then x of f, excess of f, looked like this. Yes, now I'm going to summarize the whole lecture. We got the formula of discrete time Fourier transform, which was x of f equal to summation, actually excess of f, x of nts e2 minus j 2 pi f nts. Yes, and we also understood the relation between excess of f and x of t, which is the original analog signal before it was sampled to x of nts, which was excess of f equal to summation x of f minus nfs, assuming that fs is 1 over ts. And now let's do a simple example to apply the DTFT. Assume we have x of nts like this, 1 and 1. That's it. So we have at 0 and at 1. This is NTS, it's just called NTS. Okay, so if we apply x of the formula of DTFT, we get excess of f equal to this summation, but x of nts is always 0. It's always 0 for all n values except for n equals 0 and 1. So when n equals 0 and 1, we get 1 plus 1 times e2 minus j2 pi f, and ts is equal to 1 and n equal 1. This is ts. So this is the spectrum of this discrete signal. And what is the spectrum of the original signal that this discrete signal were derived from? Okay, the answer is a one cycle of this repeated spectrum. If we plot this, let's just plot excess of f. It is, I plot the absolute value of 1 plus e2 minus j2 pi x. So this is the spectrum. It's obviously repeating itself, and we say that the original spectrum of the analog signal is just one cycle of it. Okay, so we are taking this bandwidth from -1 to +1. So obviously x of f was this only, from -1 to +1. Okay, we can define it analytically as 1 plus e2 minus j2 pi f if f is greater than or equal to -1, less than or equal to +1, and 0 else. And to recover the original analog signal, x of t, you can simply take the inverse Fourier transform of this, x of f. Yes, actually it's difficult to evaluate. I think it will be something like this. Yes, these are these two samples. I don't know. Now, in the title of this video, I said we are going to talk about the DFT, but what we did actually is that we talked about the DTFT. So the DFT, I think I'm going to merge it with the FFT video because they are very related subjects. And by the end of these videos, you're supposed to be able to plot any spectrum using maybe MATLAB. Yes, I'm going to do tutorials about them. Yes, but that's it for now. Goodbye.